Hello everyone, this is Muhammad from Reinforcement Learning and Artificial Intelligence Lab at the University of Alberta. Today I'll be presenting learning to dock robustly. So, docking is a complex task. We witnessed the first example of learning how to dock from real experience in Mahmoud and others 2018. However, their work was limited in the sense that their learned docking only worked from simplified starting positions. So as you can see, the starting position will be around here, and then it will go from there to the charging station. So they presented in their work the SenseAct framework, which included several tasks on hardware. So we have here the Create2 Docker and Create2 Mover. The Create2 Docker, the purpose of that is to dock successfully from some special starting positions, and the Create2 Mover is to move in the environment without bumping into obstacles. So in this presentation, we describe how to surpass this limitation and achieve a learned and robust docking behavior. But first, we start by describing our setup. So we had a similar setup. So we have an arena size of 91 centimeters times 82 centimeters, made of cardboard. So this is a top view from our environment that is installed in my apartment. So yeah, working from home. We have an onboard computer. So as you can see, this is a Jetson Nano, NVIDIA Jetson Nano, and we have the docking station fixed in the arena, as you can see right here. Okay, and also we have a Wi-Fi module to control the robot from a remote machine. So the hardware. This is Create2 robot. It is a differential drive robot that has two wheels with two motors, but also it has other sensors like the IR receiver. So the IR receiver will receive three kinds of signals from the charging station. It will receive a signal from the green buoy, the red buoy, and the force field. Okay, and then we have the right bumper and left bumper that will tell the agent when it bumps into things, and we have the distance sensor which will tell the agent the distance to the nearby objects, and we have 6 of them. As for the observations, the observation vector is 14-dimensional. We have distance signals, bumping signals, IR signals, docking signal, and previous action. Docking signal will the agent will receive it when it docks at the charging station. We included the previous action to add to make the agent state more Markovian, and our action space is continuous and consists of the right wheel velocity and the left wheel velocity. So the idea, how do we achieve robust docking? So robust docking, as mentioned, is quite complex. So we reshape the behavior by changing the reward at different stages to make the agent focus on one problem at a time. So we see things as follows. this is the first behavior that the agent should have. So moving behavior, and then aligning behavior, so it can start from anywhere in the environment and then align itself to the charging station. And then docking, it will start from anywhere and then align itself, and then from there it can dock. So we will create two tasks, mover task and a docker task. So the mover task will be this kind of behavior, but the docker task will be these two behaviors. Okay, and we're hoping to transfer the behavior and representation from the mover to the docker. Okay, so the docker will start by utilizing the behavior from the mover and then get it reshaped by the reward function. So this is the idea, but now let me describe the reward function that we have. So we have a window n, and each time step we have p sub t of x and I is the ith most recent data packet available at time step t for a sensor x. Okay, so we have x, y, z, and d. So for the x, this is encouraging reward for reaching the charging station. Okay, so it is pt of charging an I, and we average over a window of size n. Y of t would be the pumping penalty, and also we do the same thing here. Z of t is the distance reward, so it will be encouraging the robot to move forward. And then d is the difference in the right and left IR sensor, so it would be penalty for any difference that the robot can find. So this would motivate the agent to align itself. So this might exist or might not exist. So when it does exist, then this would be the reward. But when the robot is far from the charging station, then it would get this reward. It would be the maximum difference, but with a minus sign. So we have, so these are the components of the rewards, but we have the two different rewards for our two different tasks. So the docker task and the mover task. For the mover task we have y and we have z, but for the docker task we have the sum of all of them. So, and the only difference between the two tasks, the mover task and the docker task, is the reward function. As for the algorithm that we used PPO with normalized observation and rewards. And our hyperparameters are as follow. We have two hidden layers, 32 units each. We have this step size and so on. And the policy is parameterized as a Gaussian distribution, where the mean of the output, where the mean is the output of the network. So this is the network. So this is the observation, and then the output would be used as the mean of the Gaussian distribution. Again, we design two tasks, mover and docker, which vary only in the reward function. And after training the agent on Mover, we use the network weights of the policy and the value function as an initialization for Docker. So after we're done with the Mover task, we use the learned weights as an initialization for the Docker task. So the experiment. Training is done from scratch on hardware with Sensact framework without any simulations. Resets are done in such a way to ensure random initial pauses. So upon episode termination, create to clean routine would be called for 8 seconds, but if the agent is already docked, then it will move backward for fixed time and then call the clean routine again. Okay. An episode duration is 30 seconds and the cycle time is 35 milliseconds for both environments, and the agent is trained on Mover for 100k steps, then for 20k steps on Docker. So here are the results. For the Mover, it could solve the problem pretty quickly since the policy is relatively simple. It's just to avoid obstacles, and learning is done from scratch. So as you can see, this is after 2k steps. It can just move near to random, but after 100k steps it can solve the problem pretty good. So the Docker, after 260k steps, it could successfully align itself from any position. So we have here 6 different starting positions, and it would go from that starting position and it will align itself successfully. And it start learning from the weights learned by Mover. Okay, so this is not learning from scratch, so we utilized the weights from Mover, learned by Mover. But after 420k steps, it could successfully dock itself. So as you can see in these videos, it can start from anywhere and then it would align itself and then it would try to dock, as you can see. Okay, so quick comparison. For our approach, we have no assumptions on the initial pauses, so the agent can start anywhere in the environment or in the arena. In contrast to Sensact's implementation, which assumes special initial pauses, so the agent will start somewhere near here and then will go to dock. We have simplified rewards compared to Sensact, which contains hand-engineered rewards. But our approach needs more samples, about 1.7 more samples. And also it depends on how well the behavior and representation of the Mover task is. And this is a limitation for our method because the docking behavior will start from the Mover behavior, so the Mover behavior should have good representation and behavior for the Docker to utilize it. But on the other hand, Sensact learns from scratch. But in our case, we have, as mentioned, we have more robust docking because it can dock from anywhere in the environment. So conclusion, Transfer learning can be used to utilize the behavior and representations to make learning faster. Complex problems can be solved by dividing them into smaller ones. And the future works, we're planning to stage learning into 3 tasks: move, align, and dock, to improve performance and make sure each problem is completely solved before moving to the next one. And also we're planning to test for generalization in open arenas. So thank you.